The question is that two identical masses are going to collide and they are not colliding head on. That means if this mass is moving in this direction with some velocity u, the center of the other mass, it does not lie on the line joining their centers. The line joining the centers is this. So this is oblique collision and this is, let us say, at rest. And we have to show that if the collision is not head on, that is oblique collision takes place, the two bodies goes at right angles to each other. Okay, let us take this as our reference line, and the body just at the time of collision, it has a velocity u and the other one was standing exactly here. So as it was at rest, so it receives an impulse in this direction, so no doubt it starts moving along this direction. And the first body, let us say it starts moving along this direction and the velocities are v1 and v2. And for the time being, let us take this angle as theta 1 and this angle as theta 2. That is, theta 1 angle with the reference line the first body's final velocity is making, and theta 2 is the angle made by the second body's velocity with the reference line. So there is absolutely no influence on the system from the external influence. Therefore, we can say that along the direction of incidence of the ball, we can conserve momentum. That is, mu will be equal to mv1 cos theta 1 plus mv2 cos theta 2. This is first relationship along this reference line, and along perpendicular to the reference line, there was no momentum. So final momentum also it will be 0, and this will be mv1 sin theta 1 minus mv2 sin theta 2. What we do is change the sides and let's find out either v1 or v2. That is, v1 is equal to v2 sin theta 2 divided by sin theta 1. And another one, let's take it second, the coefficient of restitution, which is 1. The coefficient of restitution is always along the common normal. So the relative velocity of approach will be u cos theta 2 just before collision along the common normal, and the relative velocity of separation along the common normal will be v2 minus this v1's, this component is v1 cos theta 1 plus theta 2. And as this is 1, let's change the sides. We have v2 minus v1 cos theta 1 plus theta 2 will be equal to u cos theta 2, let it be third. Now we have to manage these three equations in order to find out the angles or some result between the angles. Okay, let's put second in first. The second one, v1, I am putting in first. So putting second in first, we have u is equal to v2 sin theta 2 divided by sin theta 1 cos theta 1 plus v2 cos theta 2. You are able to see that if I take v2 common, it will be cos theta 1 sin theta 2 plus cos theta 2 sin theta 1 divided by sin theta 1. From there, v2 is equal to u sin theta 1. This sin theta 1 goes there, and in the denominator we get sin theta 1 plus theta 2. And also, as v2 is ready, we can put it here and find out v1. The v1 will be equal to u sin theta 2 divided by sin theta 1 plus theta 2. Now let us put these v1 and v2 in the third relationship. So putting in third, what we get is v2 and v1 we are putting, we have u sin theta 1 divided by sin theta 1 plus theta 2 minus u sin theta 2 divided by sin theta 1 plus theta 2, and we have cos theta 1 plus theta 2 also in this term, and this side it will be u cos theta 2. Let us take this in the denominator and transfer that, and let's change the sides also. So we have sin theta 1 is equal to sine theta 2 times cos theta 1 plus theta 2 plus sine theta 1 plus theta 2 times cos theta 2. So what we get is very simple. Sine theta 1 is equal to sine theta 1 plus 2 theta 2. These angles are not equal. So this implies the sum of the angles must be equal to 180 degree. And from there it is very easy to understand that 2 times theta 1 plus theta 2 is equal to 180 degree and theta 1 plus theta 2 is equal to 90 degree. Now it is very easy to conclude that the theta 1 plus theta 2, if it is equal to 90 degree, that is the angle between the final velocities v1 and v2 just after collision is 90 degree. Hence the two bodies, they go at right angles to each other after collision.